Okay, in this problem we had to figure out what force is pulling up on A and on B. We're assuming that we have a meter stick here, and so the numbers that are on the meter stick are the numbers that are on the meter stick. And again, we figured that we have a total translational torque up and down is going to equal to the rotational torques are also going to be equaling out. So the only trick is to, what do I do with the mass of the ruler itself? Well, again, the mass of the ruler itself is going to act like it's at the midpoint, so that would be at 50, and it's going to pull down. And what you do is you just pretend that the weight of the ruler is in fact another weight that's hanging down right at 50. And if you do that, then you can kind of ignore this part over here, and it becomes a little easier to visualize, I think. So again, total down has to equal the total up. So here we know that A plus B has to equal the total going down, which is going to be 2 and 3 make 5, and 2 and 4 make 6, 5 and 6 make 11, and the 0.5, so that has to be a total of 11.5 kilograms has to be pulled up by A and B. And again, eventually we'll change these into newtons, but for right now we'll just leave everything kilograms because we're looking for the force involved here pulling up on A and the force involved pulling up on B. So we know that the total force, if we're going to use G as 10, then the total force is going to have to be 115 newtons for A and B combined. So we've got that made. Now, we have to look at, well, how much of that 115 is at A and how much of that 15 is at B. And the way we do that is by figuring out that we're in torque equilibrium also. If we're in torque equilibrium, then we have to pick a point. We can pick any point we want. It makes most sense, again, since we have two unknowns, A and B, if I pick one of those as my pivot point, then that makes the distance for that individual one 0. So if the distance is 0, then I got it made. I really leaves me only one unknown. So if I'm going to use this as my pivot point, which means this one is going to torque me counterclockwise, and B is going to torque me counterclockwise. On the other hand, that means that this one's going to be a clockwise torque, that's going to be a clockwise torque, that's going to be a clockwise torque, and that's going to be a clockwise torque. Which means, again, my total clockwise has to equal my total counterclockwise. So again, I have to measure these from the pivot point from 20. So the 2 is going to be, it's at the 10, the pivot point's at the 20, that's a distance of 10. And then my B force, the B force, I don't know what B is, but I do know that, again, my pivot's at 20 and B is at 80, that's a change of 60. So I've got that on that side. If I look at the clockwise side, well, I have the 3 is from 20 to 40, a change of 20. And then the 0.5, sorry, I'm going to plus here, 0.5 of the 50 to 20 is a change of 30. And then the 2 is at 70, 70 to 20 is a change of 50, or a distance of 50 away. And then the 4 is way the heck here at 90. 90 is 70 away from the 20, so this is 70. So now all we have to do is solve for B. And again, if we do this, 2 times 10, of course, is 20, plus 60B equals, and then 3 times 20, of course, is 60, and half of 30 is 15, and 2 times 50 is 100, and 4 times 70 is 280. So then we just add those puppies up. So 60 plus 15 plus 100 plus 80 is a total of 455 going this way. And that's going to equal, again, the 20 plus 60B. And so I want to subtract 20 first. And that's going to give me 435 equals 60B. And then to get B, of course, I want to divide both sides by 60. And so 435 divided by 60 gives me a total of 7.25 equals B. And again, we were dealing in masses here, not weights, and so we just multiply that by 10. And so B must be a total of 72.5 newtons. So that's how hard B is pulling up. And again, we said earlier that the total of A and B was 115 newtons. So if I have 115 newtons minus the 72.5, then A must be pulling up with 42.5 newtons. And so that's all you had to do for that one.